Hello friends, good afternoon and welcome to EduSat live lectures. Dear friends, today in physical chemistry we will be talking about phase equilibria. To discuss this topic we have with us our subject expert Dr. Amit Kumar. Dr. Kumar is Assistant Professor, Department of Chemistry in Dayal Singh College, University of Delhi. Without further ado, I would like to welcome Sir to our studios and request him to start the lecture. Welcome, Sir.
Thank you so much. First of all, I wish very good afternoon to all to your viewers. This is Phase Equilibria. We are starting with another fresh topic. Basically, this topic relates to third semester of Physical Chemistry course of BSc Honours Chemistry students in choice-based credit system, CBCS system. Basically, in the second semester, students would have learnt laws of thermodynamics. The thermodynamics whole course was based on conceptualizing different state functions and looking at their interpretations, looking at their possible applications. An understanding of thermodynamics was essential. There it was pointed out that the understanding of thermodynamic subject is essential to predict the feasibility of or spontaneity of a physical process or a chemical reaction. Apart from that, there are many physical processes. If you will look at it in the general definition, applies to many different kind of transitions, and one such transitions are phase transitions. And so therefore, based on the prior knowledge of thermodynamic subject, so we start with a fresh topic called phase equilibria. Now, if we need to study phase equilibria or if we need to study any other topic, we should first of all understand the meaning of the topic itself. For example, we are dealing here in this course is phase equilibria. Like in order to understand any of the topic, we need to bifurcate the topic into all the contents of the topic itself. For example, since we are dealing with phase equilibria here, it contains two words. One is phase and one is equilibria. So we must understand first the meaning of the concept of phase, and we should also learn the concept of equilibria. We are little familiar with the concept of equilibrium when we studied chemical thermodynamics there in our second semester course. But now phase is a term we invariably and interchangeably use for representation of physical state of a system, and that we do basically for the pure substances, so that make no problem. But the fact of matter is when we deal with heterogeneous systems, the mixtures, then it becomes it poses a difficulty when we interchangeably and invariably use the term phase and physical state without considering their inherent meaning, their application where they should be applied. So with that view, let us first understand what is basically a phase, or we should have the concept of phase itself. What is a phase? Let us have a look at the definition of phase. A phase is a homogeneous, physically distinct portion of a system which is well separated from other portions or parts by definite bounding surfaces. What it does mean, if we have a system, it may have several portions which are homogeneous by themselves, but when we consider the system as a whole, it will then be a heterogeneous system. Heterogeneous systems means it would be having different physical states too. If we say it correctly, then it should be there that it would be having different phases. What is the meaning of phase? Then it comes out to be that the phase is a homogeneous and physically distinct portion of a system which is well separated from other portions by definite bounding surfaces. If we need to understand this definition, we need to look at what is basically a homogeneous portion. A homogeneous portion basically is a portion of the system that is called homogeneous when it has same physical properties and also identical chemical composition throughout the whole portion. Suppose for example, if we have a system, in the whole system we find that we can draw material from any site within the system, then the physical properties as well as the chemical composition should be same throughout in all the portions. If this is so, we will have just one homogeneous system. So it means there will be one phase. So if we want to identify number of phases present in a system, then we should look at such portions within a system which are homogeneous, which are physically distinct, which are also having definite bounding surfaces. So with this clarity of definition, more emphasis we can draw on and we can have more understanding about how to determine number of phases in a system just by taking, that would be possible if we take several examples to discuss. So when we take up some examples, we will get to understand more clearly about what is actually a phase and how it actually we can determine the number of phases present in a system. Let us first of all consider, if we consider only a pure substance, suppose in our system there is only a single pure substance, such a system is called single component system. So if a pure substance we have in our system, if we make use of the terms such as phase and physical state, then it makes no difference to us. For example, in a beaker or in an evacuated vessel, if we place ice, that is solid water, as well as liquid water, then after some time, because of the temperature, they will come to equilibrium state with the water vapors as well. So basically all three different water is present within the system in all three physical states, and all these three different physical states basically are said to constitute a different phase. So it does mean that the concept of phase or the term phase and physical state is same if we make use of, or if we use these terms to describe only single component pure substance systems, or systems which are having only pure substances or in which there is only single component is present. So in that situation, it is okay with us if we make use of interchangeably and invariably the term phase, then it will make no difference to us. But if we do keep on committing same kind of things to describe the systems which are mixtures, then there may arise a problem if we say if we interchangeably and invariably use these two terms, phase and physical state. So it means we should consider mixtures first of all in order to understand the precise meaning of phase and physical state, or if we want to at all to differentiate between the two. So in general we can understand about the definition of a phase is, it is a homogeneous physically distinct portion of a system which has same physical properties and identical composition throughout the portion of the system. So that is very important to understand. It does mean that we should try to identify such homogeneous portions within the system. If there is only one such portion, it means the system has only one phase. If there are more than one such portions, it means then the number of phases will then be equal to the number of such portions being present in the system. That is how we can determine the number of phases being present in the system. If we look at it in a different manner, the phase is a portion of the system that has uniform physical and chemical characteristics. So two distinct phases in a system have distinct physical and chemical characteristics, as we have said, that we can only consider that portion of a system as phase which has uniform physical and chemical properties. So we can say it other way around. Any two different distinct phases in a system therefore should have distinct physical or chemical characteristics. Now an example we can make use of, if we have in a beaker, if we place some liquid water and we also add to this is some ice cubes, and these are separated from, since there is a finite boundary between ice cubes and liquid water. So, both these are separated by way of definite bounding surfaces. So, therefore, these do qualify, these two portions, the ice as well as liquid water, although they have same substance being present in both the portions, but these two portions do qualify for them being called as different phases, because ice, the solid water, has different physical properties compared to liquid water. So, therefore, ice, the solid water and liquid water are considered as two different phases. Since, as I said earlier, since in both the phases there is only one substance, single substance, that is water. So, water being present in solid phase is called as water being present in solid physical state, and water being present in liquid physical state means there is liquid phase. So, for pure substance we can make use of the term phase and physical state interchangeably and invariably. It will not make no difference to the real meaning of the sense. And it is more important to understand that a phase, it clearly mean that if we deal with mixture, it is not always true that one single phase will have only one particular substance. It may have more than one particular substance. So, we will also discuss this aspect. Now, the question is, it is now, as I have made it clear, that we should identify the number of homogeneous portions which have identical chemical composition and which are having distinct physical properties which are same throughout such portions. So, all those portions would then be qualified to be called them as different phases. So, we should understand, we should try to look at identifying such number of portions which are homogeneous, and therefore, those number of portions would be called as different phases being present in the system. So, let us have a little review of or a distinction between the physical state and phase once again. Phase we have defined now. Now, let us have a look at the term physical state again. Although we have been having this interpretation in our first semester course also in physical chemistry and 12th standard also, but now just have a look at it in once again with a fresh viewpoint. So, physical state basically is just a term which is used to describe the aggregate of matter. That means we all know that matter exists under standard conditions. It may exist in three different phases, either is solid or is liquid or is gas. So, basically if matter aggregates to form one physical state, that is solid, in which the chemical species occupies different interstitial positions and their positions are fixed. In liquid state their positions may not be fixed, but there is definite and greater forces of interaction which do operate between them, and in gases each of the constituent chemical species move independently of the other, although they have some weak van-der-Waals forces of interaction between them. So, mobility of chemical constituents being present in gaseous state is greater. So, this is how we just do define three different physical states of matter. So, what I mean to say is physical state only refers to the aggregate of matter, how the matter aggregates in under given conditions, under given thermodynamic conditions such as temperature and pressure. However, phase has nothing to do with only the aggregate of matter, but rather it looks at only the homogeneous portions within the aggregation of matter. What I mean to say by this, that I would like to clear it by taking several examples. For example, if we have a beaker, if we add to this beaker some sodium chloride solid, and to this we also try to add some cane sugar, that is sucrose. Then sucrose molecules are different from those of sodium chloride. Sodium chloride is ionic crystal of sodium and chloride ions, whereas sucrose is an organic molecule. One is their chemical characteristics are different. So, although both are in solid physical state and are being present in same beaker, that is same system, but the chemical characteristics of the two solids are different. In addition, they cannot make a solid solution, they cannot be miscible and at the molecular level or ionic level or the atomic level. So therefore, each solid substance is characterized by its definite characteristic structure in the solid state, and hence, as we all know that chemical structure is governed by electronic properties. So every solid substance which has distinct chemical structure would be governed by different electronic properties, and it is the electronic structure which determine the chemical structure, which in turn determines physical properties. So it does mean that every constituent solid species, unless a solid solution is formed, will be having different physical properties. Moreover, it may have different chemical composition as well, or the chemical composition can also be the same. Even if the chemical composition is the same, then the physical properties will be different. Now let us look at the the definition of a phase. A phase is a physically distinct homogeneous portion of a substance which has same physical properties throughout the portion and has identical chemical composition. Now look at our example again. The beaker which contains solid sodium chloride and solid sucrose molecules. Basically, both sucrose and sodium chloride will have different physical properties because their chemical nature is different. Not only that, electronic properties are different, and so therefore these are two different solids, and two different solids will therefore now they qualify to be called as different phases being present in the system. So it does mean if we have a system which is present only in one physical state, that is solid state. I agree that in our system there is only one physical state, that is solid state, but how many phases? Two phases. So that is what I wanted to highlight upon. If we deal with pure substances, we may interchangeably, invariably make use of the term phase and physical state. It will not make much of a difference. It will not make even any difference. But if we deal with mixtures, then the number of phases and the physical state, that will give a different meaning. So what I would like to point out to you is that physical state refers to aggregation of matter. In our example, physical state of system is only one, that is solid physical state, because we have taken two different solids. But since two different solids were there, they were both having two different set of physical properties, their chemical composition was different. So therefore both the solids do qualify them to be called as two different phases. So although this system, that is which contains solid sodium chloride and sucrose, this do qualify to be called as having two different phases, but will have only one physical state, that is solid state. That is what I wanted to highlight upon, that if we deal with mixtures, we cannot make use of the term phase and physical state interchangeably and invariably just to give the same meaning. So what we should do? We should make use of the two terms phase and physical state with lot of caution, depending upon the context in which we are making use of these two terms. So, in nutshell, phase, the term phase applies to such number of homogeneous physically distinct portions which are present in the system, which have same physical properties and chemical composition. And physical state relates to or refers to the makeup of the system. What is the, how the matter aggregates within the system, that is what I wanted to highlight upon. So, now I think with this discussion, the concept of physical state and phase, the distinction between the two concepts would have been made clear. Right, having said so, the question arises how to identify the number of physical independent phases in the system. So, if we want to do that, then let us have a look at the one example, how we would like to have a look at this, our understanding what we have developed till the point of time. Suppose we have in a beaker only liquid water, it is full and it is closed as well, we have only one liquid phase as well as physical state. If we add ice cubes to it, there is this system. Now, this has liquid water as well as ice, so there are two phases and two physical states also. If we make it if we empty the container, then the liquid will vaporize and will form vapor also, and then three phases will be there and three different physical states would also be there. So, we would call it a homogeneous system. System consists of one phase if there is only one phase being present in the system. We would call our system to be in the state of heterogeneous. We would call it a heterogeneous system if the system has more than one phase. Now, identification of number of phases in a mixture is being based on discussion of whether what is the physical state of the system. First of all, we should understand, let us segregate them in three different types. If our system is completely gaseous system, that means there may be more than one chemical constituent being present in the system, but all these constituents are present in gaseous state. So, therefore, we will have only a gaseous mixture in that situation. If we have only a gaseous mixture, a simple example of such a mixture is that if we have a container and we can close it with a lid and there is air being filled, and air, a composition of air we all know, there is nitrogen, there is oxygen, there is carbon dioxide, there is hydrogen, and there are certain other gases too. So, therefore, there are a number of gases, but we all know that gases are miscible in all proportions. So, we can withdraw the air or gases mixture from any site within the system. Its composition will always be same. Since its composition will always be same, since it is a mixture, so its physical properties will always be the same altogether in all portions. So, completely gaseous systems will have only one such portion which would qualify to be called as one phase. Since the system is homogeneous, it has same physical properties and identical chemical composition throughout the system. So, if we have only gaseous systems, it will always have only one phase, since gases are miscible in all proportions. Now, coming over to liquid systems. If we have only liquid system, that is only the physical state of our system is only liquid, then the identification of number of phases is being based on the fact that we should identify the number of liquid layers. The number of liquid layers being present in the system, each such layer will have different physical properties as well as chemical composition, and hence each such layer will be a homogeneous portion of the system, and hence each such layer would qualify to be called as different phase. So, if our system contain only liquids, then we should try to look how many liquid layers are present. For example, if we mix water and alcohol, there are two constituents, or we can say two components also, because they do not react. So, therefore, when they are placed in a mixture, So, they are miscible in all proportions. There is no, we cannot identify whether water is in this portion or alcohol is in this portion, or there are not two different layers which do form. You can mix them, mix water and alcohol in any proportion, they will always make a homogeneous mixture. Since there is only one portion which is homogeneous, physically distinct, so there is only one layer which would qualify to be called as phase. So, in a mixture of water and alcohol, there is always a single phase, as well as single physical state also, liquid state. Now, coming over to a point, if we have a mixture of water and carbon tetrachloride. Carbon tetrachloride is an organic liquid, and we all know the concept of like dissolve like, that a non-polar molecule, non-polar chemical entity would not get dissolved in a polar chemical entity. So, water and carbon tetrachloride would be having would prefer to be present in different portions as two different layers, where water will have its own physical property and chemical composition, carbon tetrachloride layer will have its own physical properties and chemical composition and hence chemical characteristics. So, therefore, we can identify there are two different layers. So, both these layers do qualify to be called as two different phases. So, therefore, now although the physical state of our system is still one, that is liquid state, because there are two liquids being present, but the number of phases are 2. That is what I wanted to point out here, is that if we deal with mixtures, then we cannot make use of the two terms interchangeably and invariably, that is phase and physical state. They will give a different meaning and a sense. So, therefore, we should make use of the context where we are making it. Okay. Now, solids I have already talked about. If we have the number of solids, unless they go to make a solid solution, there will be the number of solids would have different physical properties, would have different chemical composition, and hence each such solid would qualify to be called as different phase. So, therefore, we have in our only solid systems. If we have only one physical state, that is solid state, but if there are 4 different solids, we will have 4 phases. If there are 2 different solids, solid substances, we have 2 phases, and so on and so forth. Not only that, if we deal with allotropic modification of same substance, suppose for example, if we have graphite powder, if we put it in a test tube and we add to it some diamonds also, we all know that graphite and diamond both are 2 different allotropic modifications or 2 different crystalline forms of same substance, carbon. So, chemical composition is same in both the phases, that is only carbon, but their chemical structure in both the solids is different, graphite as well as diamond. In graphite, carbon atoms are sp2 hybridized, and in diamond, carbon atoms are sp3 hybridized. So, both these solids will have same chemical composition, but they will have different chemical structure and hence different physical properties, and hence both the solids, although both are carbon, but they will qualify them to be called as 2 different phases. So, 2 different crystalline form of same substance also would be called as 2 different phases, because both these phases will have different physical properties and different chemical structure and hence chemical characteristics. So, now I think with this discussion, the concept of phase would be more clear to you, and with this we will take on our discussion to the understanding of equilibrium, and hence we will try to understand what is a phase equilibria. Thank you so much. Dear friends, in this section we would try to see several examples where we would try to identify number of phases, and we would also try to see what is the criteria of equilibrium between 2 phases, and so we will understand what is a phase equilibria, what the topic is all about, the phase equilibria. So, with this, just let us have a look at some examples. determining the phases of various systems. So, if we have type of system, homogeneous means there is only one single phase, and heterogeneous means there would be more than one single phase. So, system is mixture of gases, as I said earlier, discussed earlier, air, which is mixture of nitrogen, oxygen, carbon dioxide, and so on and so forth. Because gases are all miscible in our proportion, they constitute only one phase. Now, mixture of two miscible liquids, ethanol and water, we also did take up, there is only one liquid phase. Water carbon tetrachloride also two liquid phases, because they are immiscible, they make two liquid layers. So, therefore, this is not a homogeneous. Third one is not example of homogeneous system, but is an heterogeneous system. So, this should be corrected here. Now, coming over to equilibrium mixture of solid and liquid water, ice and water, it is again a heterogeneous system, it is not a homogeneous. So, first two are homogeneous systems, the next two are heterogeneous system. Then we have mixture of solid and liquid and vapor, ice, water and liquid water and vapor, water vapor. If we have in a vessel, then it means we have three different phases. Then there is heat. There again, let us consider another heterogeneous system in which there is mixture of two solids and a gas. You would have noticed that if we take calcium carbonate, that is and when it is decomposed, it gives calcium oxide and carbon dioxide. So, there are three different substances which are also being present in three different phases. As I told you, the number of solids being present in a system, they all constitute each of the different phase. So, if we have in our system calcium carbonate solid phase, calcium oxide solid phase, so both these solids will constitute two different phases. In addition, carbon dioxide in gaseous physical state will also constitute another phase. So, therefore, all three chemical species would then be present in three different phases. So, we have total number of phases as 3, and such a system is heterogeneous system. Then mixture of partially miscible liquids. If partially miscible liquids are those ones which are miscible in some proportion, not in all proportion, but only in several proportions. So, if there are two different liquid layers, for example, in the situation of 65 mole percent phenol and water system, there are two different liquid layer and system is heterogeneous. So, last one is again here need to be corrected, it is not homogeneous, it is heterogeneous. And if water and phenol are present, its composition is 85 mole percent phenol, the water is miscible in phenol in this proportion, and hence this constitute only one liquid phase. So, basically we should understand now with this concept of phase in mind, we should understand phase equilibria is just nothing but the study of equilibria between phases, and phase equilibria and phase transitions occur widely in nature, in world around us. For example, boiling of liquid water in a tea kettle to the melting of Himalayan glacier. In boiling of water in a tea kettle, we observe phase transition of liquid phase in water in liquid phase to water in water vapor, and at Himalayan glaciers, great Himalayan glaciers, there is solid water, that is ice, which is being present, which undergo melting to form liquid water. So, there also we have phase transition, solid to liquid phase transition. So, in addition, we must look at water cycle, which plays a very key role in the ecology of the planet and nature. Water from various water bodies, sea, lakes, rivers, this do undergo evaporation because of scorching heat of sun, and this lead to evaporation, then the collection of water vapor occurs and condensation of them, they go to make clouds, and thereafter rainfall is observed. So, this is a water cycle. All this basically is based on phase transitions. In addition, there are various laboratory and industrial applications of phase transitions, which include distillation process, the precipitation process, the crystallization process, the adsorption of gases on surface of solid. That is also a process of phase transition. A gaseous species, when get adsorbed on surface of solid, become part of the solid surface, and therefore this adsorption process, we all know it serve as important heterogeneous catalyst systems and carry out a number of chemical reactions for us. So, therefore, industrially also phase equilibria and phase transitions play an very important role. So, we should understand that phase equilibria is the study of equilibrium between phases. That is what we should look at. And study of equilibria between phases, when we carry out, we should understand we should understand that there should be some criteria of such an equilibrium between those phases. Now, so therefore, let us have a discussion of how the equilibria between different phases of a substance do establish. Now, here I would like to point out to you is that we must understand, since this phase, the whole topic, the content matter of phase equilibria is present in 3rd semester physical chemistry course. So, the 2nd semester physical chemistry course of chemistry honors students, for BSc honors chemistry students in CBCS, they have studied thermodynamics. So, all the discussion of phase equilibria basically is based on knowledge and equations which we have developed in the subject matter of chemical thermodynamics, and so is what we are going to talk about now, that is criteria of phase equilibria, that is also being based on the various equations being developed in the subject matter of thermodynamics. So, let us have a look at what we have to deal with in development of criteria of equilibria between phases. Now, for a system, only if we have only a pure substance, then it would be called as single component system, as I have already pointed out. The chemical potential is represented for such a substance, the chemical potential is represented by symbol mu, and it's also called molar Gibbs free energy. As I have already discussed in our thermodynamics section, that chemical potential mu is molar Gibbs free energy for a pure substance and partial molar Gibbs free energy for a substance which is present in a mixture. So, here since we are considering only a pure substance, so chemical potential is nothing but molar Gibbs free energy, that is Gibbs free energy of the system divided by number of moles of the substance being present in the system. Now, consider the fundamental equation that we have that relate the change in Gibbs free energy, that is dG equal to minus S dt plus VdP. That is what we had developed as fundamental equation in our thermodynamics 2nd semester physical chemistry course. Now, this equation relate the change in Gibbs free energy with respect to change in temperature and change in pressure. Now, if we divide equation 2 by n, the number of moles, then what we get is dG by n equal to minus S by n dt plus V by n dP. So, what we get ultimately is, if we make use of equation 1 which says G by n is nothing but mu, that is chemical potential. So, if we make use of equation 1 in equation 3, what we get is dG by n, that is d mu, equal to minus S by n is Sm, that is molar entropy, into dt, plus V by n is Vm, that is molar volume, into dP. Sm is the molar entropy and Vm is the molar volume of the substance under constant pressure. If we keep the pressure constant, then there will be no change in pressure. If there is no change in pressure, then dP is 0. If dP is 0, then d mu equal to minus S dt plus Vdp term vanishes, because dP is equal to 0 in that situation. So, d mu equal to minus Sm dt under constant pressure conditions. That is, if we keep the pressure constant, chemical potential will change only depending upon the change in temperature. If temperature changes, then only chemical potential will change. Okay. So, d mu p, which is nothing but the change in chemical potential, equal to minus Sm dt. If we rearrange equation 5, what we get is, if we divide this equation 5 by rearranging in a way that we divide by dt, so it becomes del mu by del t at constant p. Now, this dt is extra, this is the term which should not be there, this dt should not be there. The left hand side should be only del mu by del t at constant p equal to minus Sm. So, this dt is written here by mistake, let it be corrected. So, therefore, what we have is this ratio, del mu by del t at constant p equal to minus Sm. This is a partial differential we must make a note of. Partial differential means because it represents the change in chemical potential of a substance being present as pure substance in a system with respect to change in temperature under condition of constant pressure. That is why we had to make use of del instead of d, and that is equal to minus Sm. So, according to third law of thermodynamics, now we should recall third law of thermodynamics. What the third law of thermodynamics says? It says that every pure perfectly crystalline substance at absolute zero of temperature has its entropy 0. So, and moreover we know that entropy increases with temperature. So, what it does mean at any finite temperature, the entropy, molar entropy or entropy of a substance is a positive quantity, and negative sign if we introduce to entropy, that is minus Sm. So, minus Sm is a negative quantity. So, right hand side is a negative quantity, so would be the left hand side of our equation number 6. So, we can say del mu by del T at constant P would always be less than 0. Here also in equation 7 this dt should not be there. So, this equation should also be little corrected. So, this differential is nothing but what is this differential? We all know that del y by del x is nothing but slope of y versus x curve. So, here we deal with as differential del mu by del T at constant P. So, what is del mu by del T? It is nothing but the slope of mu versus T curve, and if left hand side is less than 0, so it does mean that the slope of mu versus T curve is a curve with a negative slope. For 3 phases of a single substance, we can rewrite the equation 7 as del mu, that is change in chemical potential, del mu s by del T at constant P, that is change in chemical potential of solid substance with change in temperature at constant pressure condition equal to minus SMS, that is minus negative sign the molar entropy of solid. Similarly, same interpretation we can look for molar entropy of liquid, which is nothing but the rate of change of chemical potential of liquid phase with temperature, and rate of change of chemical potential of vapor phase with respect to temperature under constant pressure condition is minus SMV, that is molar negative sign of molar entropy of vapor phase. Right. We all know that molar entropy of gases is always greater, much greater than molar entropy of liquid phase, and which in turn is greater than molar entropy of solid phase. So, since mu versus T curve slope is nothing but is equal to negative of molar entropy of different phases. So, what it does means slope of mu versus T curve for gas phase is much greater and is a negative slope. Slope of mu versus T curve for liquid phase is also negative, but its magnitude is lesser than that of gas phase, and slope of solid phase would be the slope of mu versus T curve for the solid phase would be the least value. The slope of gas phase therefore is most negative, and the slope for the solid phase is least negative. Any curve which has negative slope would be tilted towards y axis if there is a curve between y and x. Here we are dealing with a curve which is between mu and t. So, therefore, the curves, each of the curves would be tilted towards mu axis, which here we can easily see. There is greater tilt, the slope of vapor phase is much steep, least slope is for solid phase, and the slope of mu versus T curve for liquid phase is in between. That is what we had predicted, and here we can see on the basis of this diagram or the graph between chemical potential and the temperature. Now, we can look at the stability of different phases of a pure substance. We must understand, and from the graph many things are very clear to us. This is the graph of or curve of solid of chemical potential versus temperature curve for solid, liquid as well as vapor. We should understand at a specified pressure, at a definite pressure. From this graph it is clear that there is a unique temperature at which this chemical potential versus temperature curve of solid phase and liquid phase do intersect. What it does mean? The chemical potential of the solid phase as well as the liquid phase at this temperature become equal, and hence the two different phases of the pure substance, the solid phase as well as the liquid phase, would come in equilibrium under such a condition of temperature, that is T fusion. FUS subscript means fuse, means fusion, that is the melting temperature or fusion temperature is the temperature at which chemical potential of solid phase become equal to chemical potential of liquid phase. Now similarly we can understand that chemical potential versus temperature curve of liquid phase intersect with chemical potential versus temperature curve of vapor phase at a temperature at specified external pressure. That temperature is called T-vap, or the vaporization temperature is also called boiling temperature. So here we will observe boiling at T-vap, and at T-fuse we will observe melting. So it should be, from the graph it should also be made very clear, it should also be made very clear that any temperature if occurs below melting temperature, only solid phase is present. Any temperature, at a temperature which is greater than the T-vap or boiling temperature, we have only the gas phase of the substance. If the prevailing temperature of the system lies in between the melting temperature and boiling temperature, then we have stability of liquid phase. That is, if our temperature of system lies between boiling temperature and melting temperature of the substance, then our system will have only liquid phase stability, only liquid phase of substance would be stable in the system. So therefore at a temperature all the way from absolute 0 up to melting temperatures, only solid phase would be present. Between melting temperature and boiling temperature, liquid phase would be present, and above boiling point, above boiling temperature, we will have only gas phase. But the fact of matter is, does this graph also predicts for us the stability of various phases? If it is a question, then the answer to this question is yes, we can. For example, and therefore the criteria, but before we discuss that, let us have a criteria, look at the criteria of phase equilibria. As I said, it is the melting temperature at which the chemical potential of solid and liquid phase become equal, because chemical potential versus temperature curve of the two phases intersect with each other, and that is how solid comes in equilibrium with liquid. So therefore, this graph makes it very apparent, for us to appreciate the criteria of equilibria between phases. If there are two phases which are in equilibrium, then the chemical potential of a particular substance constituting the phase should have the same value. That is, chemical potential of a substance in both the phases which are in equilibrium should have the same value. That is the criteria of the two phases to be in the state of equilibrium or phase equilibria. So therefore here also, so what it does mean, at boiling temperature we have chemical potential of liquid as well as vapor phase being the same, and that is the criteria of equilibrium between these two phases, and hence we observe at boiling temperature an equilibrium or coexistence of liquid as well as vapor phase. Before melting temperature we have only stability of solid phase, above boiling temperature we have only stability of gas phase, and in between the boiling and melting temperature we have stability of liquid phase only. Why this is so? Why at a particular temperature we observe a particular phase, at other temperature we observe another phase, and some other temperature we observe some other phase as well. For example, solid phase exists in a particular range of temperature, liquid phase exists in a somewhere inter between range of temperature, and the gas phase exists at the most temperature range. This occurs because if you once again look at the diagram, the curve of chemical potential versus temperature, please look at it. If we consider here this is the melting temperature. If we consider any temperature before this melting temperature, now you can see this is the chemical potential versus temperature curve for solid phase, and it is any point on this curve represent the chemical potential of solid phase, and chemical potential versus temperature curve of liquid phase if extended like this will represent the value of chemical potential of substance in liquid phase, and if we extend this vapor line, this will determine the chemical potential of vapor phase. We can easily see before the melting point, if we are in temperature range, if our system has temperature which is lower than the melting temperature, then it means at such temperature, at prevailing pressure, the chemical potential of substance in solid state is the least value, and hence only that phase would be stable which has least value of chemical potential. Between boiling point and melting point, only liquid phase has least value of chemical potential. Now you can see any point on the chemical potential versus temperature curve for liquid phase, any point on this curve represent different value of chemical potential for liquid phase between melting and boiling temperature, and hence these we can say that between melting point and boiling point liquid phase is stable because its chemical potential is the least, and above boiling temperature it is the vapor phase or the gas phase which has least value of chemical potential, and hence above vaporization temperature or above boiling temperature we have only gases or vapors phase in our system. That is, and at melting point we have equilibrium between solid and liquid phases because the chemical potential of the two becomes same, because their chemical potential versus temperature curve do intersect and chemical potential of solid and liquid becomes same, and hence two phase come in equilibrium. And at boiling temperature we have again an phase equilibria, that is equilibrium between liquid phase and vapor phase, and there we had because such an equilibrium because liquid and vapor phase has the same value of chemical potential. So now we have tried to learn with the help of this diagram that when a pure substance occur in which of the phase, when there exists equilibrium between two different phases, all such information we get from this one single diagram or a graph between mu chemical potential versus temperature of a substance. So from this graph it is very apparent what is the criteria of equilibrium between phases, two different phases. The one simple criteria, that is the chemical potential of the constituent chemical species should be same in both the phases, then only the two phases would be in the state of equilibrium, phase equilibrium rather to say. Right, having said so, now let us have a look at that if we change external pressure on the system, with that will the criteria for equilibrium for the two phases to come in equilibrium will change or not? Will the stability of different phases will change or not? That is what we need to understand. So just have a look at this. In order to understand this effect of pressure, we should try to again look at fundamental equation in the form of equation 4, that is d mu the change in chemical potential equal to minus Sm dt plus Vm dP. Here if we keep temperature constant, then d mu T equal to Vm dP. Now any phase which will have greatest molar volume will have the greatest change in chemical potential. It means gas phase there should be greatest change in chemical potential. If pressure decreases, the chemical potential would also decrease, and the least change would be for solid phase. If the molar volume follows the order, molar volume of solid phase being least and molar volume of gas phase being the most, and molar volume of liquid phase lies in between. If it is so, now you can say it means chemical potential at every temperature of solid phase should get decreased with decrease in pressure. So, you can see the black curves is being drawn at elevated higher pressure, the red curves are drawn at lower pressure. So, as the pressure decreased at every single temperature, there has been same change in chemical potential for solids phase, which has been the smallest, and for vapor phase there is greatest change. Now, you can see that this distance between the black curve and red curve for vapor phase is the greatest, least is for solid phase, and intermediate in between for the liquid phase. Now, what I said, melting temperature is the temperature at which two phases come in equilibrium, and when, or in other words, chemical potential becomes same, or in even different words, when chemical potential versus temperature curve do intersect. So, at higher pressure the black curve intersect, determine this is the melting temperature, and when red curve do intersect, this line represent the melting temperature. So, we can see if we decrease the pressure on the system, the melting temperature gets decreased, as well as there occurs decrease in boiling temperature. So, it means with increase in pressure on the system, usually we have this effect that with decrease in pressure, melting temperature gets decreased, boiling temperature also gets decreased, but because of greatest change in chemical potential on vapor phase, we observe greater change in boiling point. And if we, it means if we keep on decreasing pressure, the stability of liquid phases keep on decreasing, and there may come a temperature at which the solid phase directly coincide with that of vapor phase, and hence we reach to the sublimation curve and sublimation temperature, and at such a pressure liquid phase would not be present and solid would directly sublime. There are certain substances like water for which molar volume of liquid phase is the least rather than for the solid phase. In that situation, liquid phase observe least decrease in chemical potential, and hence melting temperature in those species increases, whereas boiling temperature decreases, and stability for such phases would decrease more rapidly compared to other such substances. So, with that discussion we come to the end of our discussion of phase equilibria. So, what we have learnt, phase is homogeneous physically distinct portion of a system which has definite bounding surfaces, and the study of equilibria between phases constitute phase equilibria, and we have also developed the criteria of phase equilibria. So, we will take up more on this topic. Till that, we say thank you so much.
On that note, I would like to thank sir for this very interesting discussion, and thank you dear friends for watching our show. Stay tuned and keep watching. Thank you.